Okay, so we're very happy to have Yudai Suzuki here to talk about the pi12 consequences of pi11 CA naught. And this is joint work with Keita Yokoyama, who is also here. And so we are happy to have both of you here to discuss this. Go ahead.
Okay, so thank you for inviting me to this seminar. I am honored to have this opportunity. And today I will introduce our paper. The title is on the pi12 consequences of pi1130. So you all can find that preprint in archive having the same name. So if you want to read the detail, then you can find the preprint in the archive. Okay, let's start. So, so in this talk, we have two topics. The first one is that we will introduce a sequence of theories in second order arithmetic such that they are structurally increasing and the union of Tn's is just the same as the pi12 sentences provable from pi11 to 0. Here, this inequality means that the set of sentences provable from T is structurally smaller than the set of sentences provable from S. And this equality means that the set of sentences provable from T is the same as the set of sentences provable from S. So first, I will introduce a sequence of theories such that it characterizes the pi12 sentences provable from pi11 0. And then I will compare these sequences and some weaker variant of Ramsey's theorem or determinacy. They are equivalent to pi11 0. So, and I will give a motivation for studying the set of pi12 sentences proven from pi11 0. It is known that there is a very large gap between ATR0 and pi11 0. More precisely, it is known that any pi12 consistent extension of ATR0 does not reach to pi11 0. However, it is known that there are some theorems which is represented by a pi12 sentence, and there are only a few results on the pi12 upper bound for them. So it means that, so for example, Menger's theorem in graph theory or Nash-Williams theorem in BQ theory or classical theorem for embedding of trees. So they are represented by a pi12 sentence and they are provable from pi11 0. However, so from this fact, pi11 0 is too strong to prove such pi12 statement. So there's a natural question that what is pi12 upper bound for those theorems, but there's only a few results for such a thing. So there's a question that what is the structure of the pi12 sentences proved from pi11 0? So, I mean, to study the structure of this set, we can give some upper bound for those theorems. Okay, so first I will introduce a sequence of theories to cover the pi12 consequences of pi11 0. So for this purpose, we use a variant of beta model reflection. So for this purpose, first of all, I recall the notion of hyperjump. So for a set X, the hyperjump of X is the set of indices of computer X computable orderings. So it is known that any pi11 set defined from X is computable from the hyperjump of X. More precisely, it is many-one reducible to hyperjump of X. So hyperjump of X is one of the pi11 complete set. So the axiomatic system pi11 CA0 is defined by SA0 plus any set X has its hyperjump. Since hyperjump of X is pi11 complete, any pi11 so, and as I said, any pi11 set computable from definable from X is computable from hyperjump. If we have a hyperjump, then pi11 comprehension holds. So pi11 comprehension is characterized by the existence of hyperjump. So, and in our formal system, we can repeat the we can apply action many times. So it means that pi11C0 is defined by any set that has its hyperjump. However, it is equivalent to, for example, any set that has its double hyperjump or its triple hyperjump, and so on. So even two theorems, A and B, are equivalent to pi1CA0. They sometimes separated in the hyperjump, in the sense of hyperjump n level. I mean that, so theorems provable from pi1CA0 should be classified into hyperjump level and hyperjump, double hyperjump level and triple hyperjump level, and so on. So this idea means that so classification of hyperjump n level is useful to give a increasing sequence which covers the pi12 consequences of pi130. Okay, so and first I explained that this intuition is realized in some sense. So let theta be an arithmetical formula such that pi130 proves this pi13 statement. Then we can find a natural number n such that S0 proves for any set X, if X has its n times hyperjump, then a solution Y of this part can be computed by the n times hyperjump of X. So it means that so pi13 sentences provable from pi1CA0 is classified into hyperjump level or second double hyperjump level or second hyperjump level and so on. And so, okay. And I comment that this was essentially proved by Montalban and Showa. So the so their result is a bit different, but we can easily rewrite their proof by default.
Yudai, can I ask a question now? You're
Okay.
probably going to tell us, but is it a hierarchy?
A hierarchy, I mean.
Right. Right, you know, so is Hn plus one weaker than Hjn?
Yeah. So,
but is it known? I mean,
so sorry, can you say again?
Okay, so you have this hierarchy of theories that, you know, one is sort of extending the next one, but do we know that the n plus first is stronger than the nth one?
So you mean?
Well, in the basic definition of the stratification.
Okay, so I will explain it later. So you mean well,
Right here,
yeah.
right.
Yeah. It's proper. It's proper.
Right. But
It forms a proper hierarchy.
And how do we know that?
Yeah. So later, I guess he will explain.
Oh, right. Okay, that's what I thought you would. I just wanted to ask now. Okay, thanks.
Actually, that is the point that so in this form we cannot separate so the level of hyperjump. So I mean, so for the Pi 1 3 part, we cannot separate the level of hyperjumps, but by taking what suitable Pi 1 2 variant of those statements, we can separate those. Yeah, okay. I will explain the detail later. So anyway, so any Pi 1 3 sentences proven from Pi 1 3 0 is separated in the n times hyperjump level in a sense. So, and actually, so Pi 1 2 sentences proven from Pi 1 3 0 also separate in so n times hyperjump level. Okay. As you know, there is a problem such that all of statement of this form for any set, there is a set y which is equal to the n-times hyperjump is pi 1 3. However, so we would like to study the pi 1 2 sentences. So for this purpose, so this form of statement is too strong. So we would like to give a pivot variant of this form, this statement. So for this purpose, we use coded omega models. Here, a coded omega model is a structure of second order arithmetic such that its first order part is the same as the ground model, but the second order part is coded by a set. So the name coded omega model is from the fact that the second order part of this model is coded by a set. Okay. So, take a coded omega model and so the importance of the omega model, one of the importance of the omega model is that for any condition sigma, so the statement M satisfies the condition sigma is a sigma 1 condition. So a formula of this form, so for any set X, there is a coded omega model M such that X is in M and M satisfies sigma is pi 1 3 because this part is sigma 1 1 and so this part is sigma 1 1. So this the full sentence is pi 1 2. So even if sigma is complicated, for example, sigma is pi 1 3 or pi 1 4, however, the statement of this form is pi 1 2. So this is a point that taking a pi 1 2 analogy of this statement. So by using coded omega model, we define our pi 1 2 variant of the existence of hyperjump, which we call beta 1 0 reflection. So beta 1 0 reflection of n is the statement of the form for any set X, there is a coded omega model M such that X is in M and M satisfies SA0 and X has n times hyperjump. I comment that this Y may not be an actual n times hyperjump. It behaves hyperjump in M, only in M. So this Y not need to be the actual hyperjump. So this statement, beta 1 0 reflection, is weaker than the statement that X has the hyperjump or n times hyperjump. However, so since M is a model of SA0, it is not so far different from actual hyperjump. Okay. So, and then, as I said, so this statement, beta 1 0 reflection, is a pi 1 2 sentence. And we can easily show that this is proven from pi 1 3 0. And so by this form, we can make a increasing sequence of theories. So I mean that, so beta 1 0 reflection of n is strictly increasing. So each beta 1 0 reflection of n plus 1 proves beta 1 0 reflection of n. However, beta 1 0 reflection of n does not prove beta 1 0 reflection of n plus 1. So, and the last class is the most important point, such that each sigma 1, pi 1 2 sentence provable from pi 1 3 0 is provable from this beta 1 reflection of n for some n. So to prove this result says that the hierarchy of beta 1 reflection of n covers the pi 1 2 part of pi 1 3 0. So to prove this result, we use this theorem. So I mean that, so it says that if AC0 over AC0, if X has the n times hyperjump, then the solution Y can be found. So, and so beta 1 0 reflection says that there is a model of AC0 plus X has the n times hyperjump. So in M, we can find a solution of given pi 1 3 sentence in the sense of this theorem. So by applying this theorem to beta 1 0 reflection, we can show that each sigma 1 to each sigma which is pi 1 2 and which is provable from pi 1 3 0 is already provable from beta 1 0 reflection of n for some n. So consider that hierarchy of theories SCA0 plus beta 1 0 reflection of n, then the sequence slice this set, the set of pi 1 2 sentences provable from pi 1 3 0. Okay. So this is the first result, and okay, so then I will explain why this assertion is called beta 1 0 reflection.
Could I add one short comment?
Okay.
Yeah. So in the previous slide, as Roman asked, the hierarchy is actually straight
Yeah.
here, and well, it's at least some parts has to be straight because the pi 1 part of pi 1 2 part of pi 1 CA0 won't be finitely axiomatizable. So of course, I mean, since these beta 1 0 reflection covers the whole pi 1 2 part of pi 1 CA0, some of them must be straight. But actually, well, one can easily check that beta 1 0 reflection n is true in the omega model of beta 1 0 reflection of n plus 1. I mean, omega model provided by beta 1 0 reflection n plus 1. So actually, the beta 1 0 reflection n plus 1 implies the consistency of beta 1 0 reflection of n. So it's properly. So this forms a proper hierarchy.
Oh, I see. So this explains much. So there are no natural statement of some kind of partition kind of theorems that would sort of do. But this shows the properness of the hierarchy. That's
right.
Yeah. So as Keita says that, so this strictness has more information like that. So beta 1 0 reflection of n plus 1 proves the omega model reflection of beta 1 0 reflection of n. So
very elegant.
Yeah. Okay, so then I return to my slide, and okay, so the name beta is from the notion of beta models. So beta model is a special case of coded omega model. So we say a coded omega model M is a coded beta model if it is sigma 1 absolute for the ground model. So I mean that for any sigma 1 sentence, the ground model satisfies the sigma 1 sentence theta is equivalent to M satisfies the sigma 1 sentence. So in this case, we say omega model M is a beta model. Yeah, so, and I remarked that, so any coded omega model is sigma 1 absolute for the ground model. Okay. So, and so there is a very well-known fact that so over SA0, the existence of the hyperjump of X is equivalent to the existence of a coded beta model, including M. So by using this fact, we can rewrite our beta 1 0 reflection as follows. This says, this statement says that for any set X, there are coded omega models, n plus 1 coded omega models such that X is in M0 and each Mi is in Mi plus 1 and Mi plus 1 is beta, I mean. So Mi and Mi plus 1 is beta means that they are sigma 1 elementary. Yeah. And the last model Mn satisfies SA0. So by rewriting the existence of a hyperjump by the existence of coded beta model, we can rewrite beta 1 0 reflection of N as follows. So the point, so the point that each Mi and Mi plus 1 is sigma 1 absolute. However, they are only sigma 1 0 absolute for the ground model. So they may be not sigma 1 absolute for the ground model. So, and the superscript 1 of beta 1 0 reflection is from the condition that each Mi and Mi plus 1 are sigma 1 absolute, and the subscript 0 in beta 1 0 reflection is from the condition that they are sigma 1 0 absolute for the ground model. So we can consider some variants like beta 2 0 reflection or beta 2 1 reflection and so on. So we can apply our study to more higher level by taking another I and j in these superscript and subscripts. But so in this talk, we consider only beta 1 0 reflection. Okay. So then, so as I said, so the hierarchy of beta 1 0 reflection covers the pi 1 part of pi 1 CA0. Yeah, so and so as I said, one of the purpose of studying the pi 1 consequences of pi 1 CA0 is to give some upper bound for like classical theorem. So I will explain that which level of beta 1 0 reflection proves classical theorems or Mega theorem or Nash-Williams theorem. Okay, so and as I said, there are only a few results on the pi 1 2 upper bound for classical theorem or Nash-Williams theorem or Mega theorem. So actually, Henry Tassner gave a pi 1 2 upper bound for those theorems. And in his work, he focused on the equivalence of the Leston surpass principle and pi 1 1 CA0. So it is known that over SA0, pi 1 CA0 is equivalent to the statement that any ill-founded tree T has a leftmost path. Here, leftmost means that leftmost with respect to the lexicographical order. So, and Henry Tassner, so since this leftmost path principle is equivalent to pi 1 C0, it is pi 1 3 sentence. So he considered a restricted condition of leftmostness. So for set for tree T and a path, infinite path f of T and a well order alpha, we say this path f is delta 0 alpha leftmost path of T if for any infinite path T of G, infinite path G of T, if G is computed by the alpha times jump of f, then f is smaller than z in the lexicographical ordering. So f may be not the leftmost path, but f behaves leftmost path in this area, in a restricted area. So the notion of delta 0 alpha leftmost path is restricted. I mean that's so. The condition delta 0 alpha leftmostness is a restricted form of leftmostness. So, and Henry Tassner introduced two types of restricted or so in his paper he said relative leftmost path, and so he introduced two types of restricted leftmost path principle called delta 0 alpha leftmost path principle and transfinite leftmost path principle. Delta 0 alpha leftmost path principle says that any finite tree has a delta 0 alpha leftmost path, and transfinite leftmost path principle says that for any well order alpha, delta 0 alpha leftmost path principle holds. And Henry Tassner proved that ATR 0 is provable from delta 00 LPP over RC 0, and delta 00 LPP is structurally weaker than transfinite LPP. And Menger's theorem and Nash-Wilson theorem are provable from transfinite LPP, and classical theorem is provable from delta 02 LPP. Okay, so we compare our beta 1 0 reflection and delta 0 alpha LPP and transfinite LPP. So then we can show that over SA0, delta 02 LPP is structurally weaker than beta 1 0 reflection of 1. And I omitted the detail, but beta 1 0 reflection 1 can be written as a variant of restricted LPP, and beta 1 0 reflection of 1 is structurally weaker than transfinite LPP, and beta 1 0 reflection of 2 is structurally stronger than TLPP. So comparing the beta 1 0 reflection hierarchy and restricted LPPs, then restricted LPP is not so much stronger in the sense of beta 1 0 reflection hierarchy. So, and also the Menger's theorem, Nash-Wilson theorem, and classical theorem is not so much different from ATR 0. So they are provable from, so they are one of the pi 1 2 consequences of pi 1 3 0. But, and so for example, classical theorem is not proven for ATR 0, but they are not so much different from ATR 0 in the sense of beta 1 0 reflection hierarchy. Okay, so this is an application of our beta 1 0 reflection hierarchy. Okay, so then there is a question that, so what is the pi 1 2 statement corresponding to the higher level of this hierarchy? So, I mean that's so well-known pi 1 2 statement is in the lower level of beta 1 0 reflection hierarchy. So there's a natural question that what is the pi 1 2 statement corresponding to the higher level of beta 1 0 reflection hierarchy? So to give some pi1 statement corresponding to the higher part, so we use some variant of Ramsey's theorem and determinacy. Okay, so I will explain the case of Ramsey's theorem. So it is known that some fragments of Galvin-Pericles theorem, like sigma 02 Ramsey's theorem or sigma 03 Ramsey's theorem, and so on, are equivalent to pi1 CA0. So, so I will explain what is sigma 02 Ramsey's theorem later, but the important point is that the hierarchy of sigma 0n Ramsey's theorem collapse in the sense of reverse mass because all of they are equivalent to pi1 CA0. However, from the viewpoint of computability theory, all of sigma 02 Ramsey's theorem and sigma 03 Ramsey's theorem should be separated. Yeah, because in the sense of computability, it's natural to think that they have different complexities. So, and we show that comparing our beta 1 0 reflection hierarchy and those theorems, we can separate those theorems in a sense. And so we can reflect the intuition of computability theory into reverse mass. Okay, so anyway, first of all, I need to explain what is Ramsey's theorem. So for explaining Ramsey's theorem, I need to introduce some notations. Okay, so first, for a set X, subset of the natural numbers, we write the bracket Xn to denote the set of the infinite subset of X. So this is all infinite subset of X. And we say a class A, which is a subclass of this set, has the Ramsey property if there exists a set H, which is an infinite subset of H, such that all infinite subset of H is in this class A, or all of infinite subset of H is not in this class A. So in this case, we say this class A has a Ramsey property, and we say this H is a homogeneous set for A. Yeah, so for short, we say A has the Ramsey property if there is an infinite homogeneous set for A. Okay, so and then it is known that over SA0, actually this equivalence holds over RC0, but so in this SA0 is enough. Okay, so so over SA0, so these three statements are mutually equivalent. So the pi1 CA0 and any sigma 02 definable A has an infinite homogeneous set, so which we call sigma 02 Ramsey's theorem, and any arithmetically definable class A has an infinite homogeneous set for its, so which we call sigma 10 Ramsey's theorem. So it is known that over SA0, all of pi1 CA0 and sigma 02 Ramsey's theorem and sigma 10 Ramsey's theorem are equivalent. So, and as sigma 02 Ramsey's theorem or sigma 10 Ramsey's theorem is equivalent to pi1 CA0, they are pi1 3 statements. Okay, so we introduce a pi1 2 variant of those theorems. So for this purpose, we introduce an analogy of Turing reduction, which we call arithmetical reduction. So for two sets x and y, we say x is arithmetically reducible to y. And if there is a natural number n such that x is computable from n times Turing jump of y. So yeah, so this is an extension of Turing reducibility. Okay, so and so the restriction of this form is very useful because we can say that x is arithmetically reducible to y is equivalent to that x is in the smallest omega model of ACA0, including y. So the condition of arithmetical, so like that. So if x is computable from y is equivalent to that x is in the smallest omega model of RCA0, including y. So and so very similar, but situation holds. So x is arithmetically reducible to y is equivalent to that x is included in the smallest omega model of SA0, including y. So if arithmetical reduction holds, then we can use omega model of SA0 in a sense. So it's very natural and useful notion of reduction. So and by using this reduction, we define a restricted form of Ramsey property. We say a class A has the relative Ramsey property if there is an Homogeneous set H in the following sense. So the all of infinite subset of H, which is arithmetically reducible to H, is in A, or all of infinite subset of H, which is arithmetically reducible to H, is not in A. So this H may be not the actual infinite homogeneous set. However, this behaves infinite homogeneous set in the smallest omega model of ACA0, including H. So this restriction is very similar to the restriction used to define the delta zero alpha leftmost path. So yeah, so and actually we can show that so this restriction can be used as an extension of delta zero alpha leftmost path principle in a sense. Okay, so and then we define the relative sigma ij Ramsey theorem such that relative sigma ij Ramsey theorem says that any sigma ij definable class has this property. Okay, so then we can show that over ACA0, each sigma 0 n Ramsey's relative sigma 0 n Ramsey's theorem is provable from beta bundle reflection of n. And we can show that relative sigma 0 2n Ramsey theorem proves beta bundle reflection of n. Okay, so and I comment that this result okay, so I comment that this result probably can be improved as follows, that over SA0, beta bundle reflection of n is equivalent to relative sigma 0 n Ramsey theorem holds. So, and this is essentially from the current work by Marconi and Marco, but okay. So anyway, we can show that. So also the actual sigma 0 in Ramsey theorem hierarchy collapses in the sense of reverse mass. However, the relative sigma 0 n Ramsey theorem hierarchy does not collapse. So this result reflects the intuition of computability theory, intuition in computability theory, like so an infinite homogeneous set for sigma 0 and large theorem is computable from n times hyperjump, and so sigma 0 n lambda theorem and sigma 0 m lambda theorem should be separated if n and n is not equal. So and so as higher level of sigma 0 n lambda theorem proves higher level of beta 1 0 reflection, so we can give we can give another hierarchy which covers the pi 1 to consequences of pi 1 3 0. Okay. So, and I will also explain that for the case of determinacy, there is a similar result for the case of Ramsey theorem. Okay, so for explaining this result, I will introduce the infinite game, Gale-Stewart game. Okay, so let A be a class of the sequence of natural numbers. So for class A, we can consider a game ZA as follows. In ZA, there are two players, 0 and 1. 0 and 1. And first, 0 plays a natural number, x0. Then the player 1 plays a natural number, x1. And then 0 plays a natural number, x2. And 1 plays x3, 0 plays x4, and so on. So after infinite steps, so this game is an infinite sequence, xi. So, and the player 0 wins the game ZA, wins in the game ZA if the yielded sequence is in A. And player 1 wins if the yielded sequence is not in A. So this is the definition of Gale-Stewart game. So it is known that the determinacy of the Gale-Stewart game in for some simple set A is equivalent to pi 1 3 0. So to explain what is determinacy, so we need to introduce the notion of strategy for a game. So we say a function is from the finite sequence of natural number to natural number as strategy. So, so intuitively, strategy means that so strategy decide how to play player 0 or player 1. So more precisely, for strategies S and S prime, a infinite sequence xi is said to be the play along S and S prime if the even part of this sequence is computed by S, and the odd part of this sequence is computed by S prime. So each play of players are computed by S and S prime. So in this sense, S and S prime decide how to play the player 0 and player 1. So S and S prime are called strategy. So we say a strategy is a winning strategy for the player 0 if S wins against any strategy for the opposite player. So if S is a strategy for player 0, then S wins against any strategy for player 1. And a strategy S prime is a winning strategy for player 1 if it's against it wins against any strategy for player 0. So, and we say a class A, which is a subclass of the sequence of natural numbers, is determined if the game has a winning strategy. So one of the player has a winning strategy. Okay, so, and we say, the assertion gamma determinacy is the statement that any class A defined by a formula in gamma is determined, has a winning strategy. So, and it is known that over SA0, so all of pi 1, 1, CA0 and determinacy for sigma 0, 1, 2 set and determinacy for sigma 0, 1, n set are equivalent. Here, sigma 0, 1, n denotes the difference hierarchy. It means that sigma 0, 1, 1 is just the same as sigma 0, 1, and sigma 0, 1, n plus 1 is of the form phi and not psi. Here, phi is sigma 0, 1, and psi is sigma 0, 1, n. So, for example, sigma 0, 1, 2 is the same as of this form. So our formula is sigma 0, 1, 2 is equivalent to that it is written as phi and not psi here, phi and psi is sigma 0, 1. So it is also equivalent to the conjunction of sigma 0, 1 and pi 0, 1. So, and sigma 0, 1, 3, sigma 0, 1, 4 is defined similarly. Okay, so it is known that over SA0, the determinants of pi 1 CA0 and the sigma 0, 1, 2 determinacy and the sigma 0, 1, n determinacy for large n are equivalent. So, and so as in the case of Ramsey's theorem, so they should be separated in the sense of computability theory. And so our beta bundle reflection achieves the separation in a sense. Okay, so to give a pi 1, 2 variant of determinacy, we define the relative winning strategy. But so this relativization is very similar to the case of Ramsey's theorem. So we say a strategy S is a relative winning strategy for player 0 if any strategy S prime for player 0, which is identically reducible to S, is fitted by S. And we say a strategy S prime is a relative winning strategy for player 1 if it wins against for all strategy S which is identically reduced to S prime. And we say the class A is pseudo-determined or it has pseudo-determinacy if there is a pseudo-winning strategy. And so we introduce the relative sigma 0 n determinacy, which is the assertion that any sigma 0, 1 n definable class is pseudo-determined. So by comparing our beta 1, 0 reflection hierarchy and the hierarchy of relative sigma 0, 1 n determinacy, then we have that. So the relative sigma 0, 1, 2 determinacy is in the intermediate of beta 1, 0 reflection 1 and beta 1, 0 reflection 2. And each beta 1, 0 reflection of n proves that sigma 0, 1 n determinacy, relative sigma 0, 1 n determinacy, and there is a certain p of n such that beta 1, 0 reflection of n is strictly bigger than relative sigma 0, 1 Pn determinacy. So we didn't evaluate P of n. But anyway, so there is a certain P of n such that relative sigma 0, 1 Pn determinacy.
Sorry, can you say now a little bit more about Pn? You didn't evaluate it, but you know it's elementary, so it comes somewhere from a proof.
Okay. I mean, that's so Pn can be written as like, so we have a very rough upper bound of Pn, but we didn't evaluate, so but strictly, so we didn't evaluate the detail of Pn, but we have that's very rough upper bound for Pn.
What was that? Do you remember 2 to the 2 to the n or something like that?
Yeah.
Oh,
I
I
don't
see. So
remember.
that's
Mm.
nice.
Not too terrible, I would say. Yeah.
Right.
So, but so we
No.
believe that this is not the suitable upper bound. Yeah, optimal upper bound. Yeah, okay. So yeah, so actually, so what is what's smallest Pn is one of our question. But okay, so anyway, so if we take very large M, then sigma 0 M relative sigma 0 1 M determinacy proves beta bundle reflection of N. So the relative sigma 0 1 M the hierarchy of sigma relative sigma 0 1 M determinacy also covers the pi 1 to constant case of pi 1 to 0. And so in this result, one of the important point is that the first class. So in the first class, the relative sigma 0, 1, 2 determinacy is not equivalent to both of beta bundle reflection of 1 and beta bundle reflection of 2. This is because that, in the first study of sigma 0, 1, 2 determinacy in reverse math, the paper by Tanaka, it is pointed that to prove pi 1, 1 to prove pi 1, 1 comprehension from sigma 0, 1 to determinacy, the base theory is SA0. So SA0 enough to the base theory for proving pi 1 C0 from the sigma 0, 1 to determinacy. However, it is pointed that SA0 is not enough to prove sigma 0, 1 to determinacy from pi 1 C0 in a sense. And so ATR0 should be needed to prove sigma 0, 1 to determinacy from pi 1 0 in a sense. So, and this result makes the situation clear. So the difference of beta 1 0 reflection of 1, so it's stating the existence of a hyperjump in a sense. And so relative sigma 0, 1 to determinacy says that, so it says that sigma 0, 1 to determinacy holds in a sense. So, and the difference of those theorems is from the difference of the base theory. So, yeah, and actually we can make the situation more clear by taking some another variant of beta 1 0 reflections. Then, so we can show that the necessity of ATR0 to prove sigma 0, 1, 2 determinacy from pi 1 C0. So, yeah, so anyway, so by taking some variant of sigma 0, 1 to sigma 0, 1 n determinacy, so we can give another hierarchy. And so by comparing beta 1 0 reflection and sigma 0, 1 n determinacy hierarchy, so we can reflect the intuition from the computability theory like that. So to compute winning strategy for sigma 0, 1 n games, we need to take some, not only single hyperjump, but we need to take some n times hyperjump. So this result reflects such an intuition. Okay, so I will end my talk with summarizing today's talk. In this talk, yeah, so first we introduced a hierarchy beta 1 0 reflection of n, which is the same as the pi 1 2 consequences of pi 1 C0. So, and some existing pi 1 2 theorems provable from pi 1 CA0, like Menger's theorem, Nash-Williams theorem, and classical theorems are bounded by beta 1 0 reflection 1 or beta 1 0 reflection 2. And there is another hierarchy slicing the pi 1 0 consequences of pi 1 CA0 according to Ramsey's theorem or determinacy. Okay, thank you. So,
Okay, let's thank our speakers. So let me open up the gallery. Thank you again, Yudai.
yeah.
And I will open up for questions. So I have a very naive question. What about just sigma n determinacy? Is that just not provable in pi 1 CA naught, or
Uh,
so just sigma n, sigma 0 n. So
sigma n.
yeah. So yeah, not without the extra subscript.
Sorry, you mean the sigma 0 n determinacy for
Mm-hmm.
so
Is this
for
not, is this not is this provable in pi 1 CA naught? Is it yeah, when is it weaker? I have no intuition on that.
so for
Even delta 0 4 determinacy is not provable in full second order
yeah.
arithmetic.
Okay.
Right. Yeah.
So delta 0, so the difference of sigma 0 3 class can be proved by the second order arithmetic, but yeah, so
Yeah.
sigma delta 0 4 determinacy is not provable from pi 1 0, and yeah, so sigma 0 2 determinacy is very similar to pi 1 2 comprehension, if I remember correctly, but they are not equivalent.
Yes.
Yeah.
Yeah.
So actually,
Yeah,
so all of determinacy is pi 1 3 statement, so it's difficult to write it in comprehension. So yeah, so but instead of comprehension, we can compare the determinacies and the existence of beta models of comprehensions. Yeah, so but
Yes.
anyway, so yeah, so over sigma 0 2 determinacy, it's so the situation is very complicated. Yeah.
Right. Okay. Thank you.
I also have a naive question, and if you could go back to the last slide.
That's right. Okay. This one.
Right. So when you have, the MT and WT and KT are bounded by this one level of the hierarchy, so it's a low
Yeah.
level, right? So so you I'm sure you have looked for other examples, but they're probably hard to find. Is there something that comes to mind? Maybe there are theorems that are so difficult to prove that no one has ever proved them yet. Because this could be something like in this whole sort of mission of reverse mathematics to go to the boundaries of what can be done and what possibly can. Have you? I'm sure you've thought about that. Have you?
Okay, so yeah, actually, so for example, I think finding some natural pi 1 2 statement which corresponding to beta 1 0 reflection of 3 or 4 by without using some indices like those. Yeah, so yeah, so it's very interesting to find some finding pi 1 2 pi 1 2 statements which corresponding to beta 1 0 reflection of 3 and which is natural in some sense. Yeah. Yeah.
Yeah, it's not so easy. But yeah. Yeah, for example, the Kruskal's theorem with gap condition, for example, going up to the higher level of this hierarchy. So I don't think it's a very natural example, but at least like
Sorry,
there are
sorry,
some.
I'm sorry, Kida, can you say that one again? Kruskal's theorem with
So the Kruskal theorem with gap condition, I mean the gap condition provided by I mean introduced by Harvey Friedman. So the something like a kind of a stronger version of Kruskal theorem.
Thank you. I'll take a look at that. Okay, any other questions?
Let's see. Ken, are you still there?
Yes.
You should have a question.
Well, I mean, I'm more, it's that I'm trying to think of combinatorial principles, but he's covered so many of them. Nash-Williams theorem. I mean, he's exhausted my range of difficult combinatorial principles. Now, like Nash-Williams is not even that, and the barrier theorem. All these things are sort of subsumed by this. And I also think, sort of historically, people going as far back as Suslin and Kleene would just be delighted at this work.
No, it is a very beautiful work. There's no question about it.
Yeah, this is really impressive.
No, maybe it shouldn't be recorded. Because, I remember there was a very beautiful talk. I was at when Stefan Todorovic was giving kind of an informal talk, like a small seminar talk when he talked about continuum hypotheses. And the gist of his talk was that, as we know that continuum can be anything we can think of, but he was sort of arguing in this direction that it's some actually specified number, and he says maybe it's Aleph 1, maybe it's Aleph 2, but he had good arguments to say that it will never be Aleph 17. Once you have a certain hierarchy and you talk about mathematical practice, that there is absolutely no reason for the continuum to be. I know, but he had something much more to say that I'm saying now. But so there's a similar phenomenon here that what we know is sort of falls into certain bounded category, and beyond that we just don't know, because perhaps those questions have not been asked at all. But maybe they are not interesting for whatever reason.
Yeah, good point.
There was a question in the chat about making the slides available. If you send them to me, then I can, or to Vika, then we can post it on the seminar website. If you're willing to make them available. This was from Thomas, who said that he has some colleagues in Wellington who would be interested in. So, if you're willing to make the slides available, you can send them to me, and I'll make sure that, yeah. And then Thomas, you can check the Near Logic website. It'll be on there in a couple of days.
Okay.
Any other questions? Okay, so let's thank Yudai again, and Keda for joining us. This was a very nice talk. Very impressive work as and with that, I believe this concludes our MOPA for this a seminar for this semester. Unless we have any last minute additions that get back to us, I guess, or if anyone wishes to provide another talk. So we will, you can stay on the mailing list, and we'll be in touch if we start again in a few months.